Okay, so when you talk about a manipulator, it has these dynamics which are non-linear, and so you cannot use a linear control. But linear control is nice because the equations are simple and there are techniques which lead you to analytic things like analytical solution. So what I'm going to do is I'm going to motivate this with a spring mass damper system. You've probably seen many of these in a course on vibrations or course on dynamic systems and controls if you've taken that. M1, M2, let's give them some spring constants. So let's say this is K1, this is K2. Let's add some force. So let's assume that you can control the force on M2. I'll call it U2 because in language of control theory, you typically use U for control. Okay, let's call, so since there are 2 degrees of freedom, let's give them names Q1 and Q2. There's one more actuator here. There's one actuator which connects the 2 masses. So U2, so U1. Yeah, first goal is to write the equations of motion. Yeah, and we'll use the Lagrange equations of motion. We've done that before, and so we should be able to do this fairly quickly. So the kinetic energy is T is half mass Q1 dot square plus half mass Q2 dot square. So that's the kinetic energy. We need the potential energy, so that would be 0.5 or half K1. So K1 would have Q1 to be the stretch in the spring, so Q1 square plus 0.5 K2. Now K2 is going to be stretched on both sides. It's connected to mass M1 and M2. So its deflection is going to be Q1 minus Q2 square. Okay, so the Lagrangian is defined as T minus V. So 0.5 M1 Q1 dot square plus 0.5 M2 Q2 dot square plus 0.5 K1 Q1 square plus 0.5 K2 Q1 minus Q2 square. Okay, so we have L, and now comes the equations of motion. So there are 2 equations. We first write the general formula. So for Q1, let's do the equation for Q1. So d dt. So we take this quantity and take the derivative with respect to Q1 dot. You can see the only term with Q1 dot is the first term. So it'll be 0.5 M1 times 2 Q1 dot minus dl dq. The only term, well, the 2 terms with Q1, it's this one and this one. So that would be 0.5 K1 twice Q1 plus 0.5 K2 times 2 times Q1 minus Q2. Okay, and the last, well, this is all equal to Qj, but Qj is the external force on 1, it will be U1. Is that right? See. Okay, U1 acts actually, so this is my positive direction. Since U1 acts on M1, it acts in the negative direction, I need to put minus U1 here. Minus U1. So taking the second derivative of this, we have M1 Q1 double dot minus K1 Q1 minus K2 Q1 minus Q2 correct? I think I made a mistake here. So this is negative V, right? So this should be, my bad, this should be negative, this should be negative. Won't change much, but this thing here would be positive because this negative times this negative is positive. So this ends up being positive, positive. Okay, so I'm going to rearrange this equation and write it in terms of Q1 double dot. This is minus K1 M1 plus K2 M1 Q1 plus K2 M1 Q2 minus U1 divided by M1. Okay, so let's take Q equals Q2, and so we need to evaluate d dt dl dq2 dot minus dl dq2 equals qj or q, sorry, capital Q2, which is the external forces. So d dt, okay, the derivative of L with respect to Q2 dot. So there's only one term here which has Q2 dot, and that's this term. So the derivative of that would be 2 times Q2 dot minus dl dq2. We see that the only term which has Q2 is the last term. So this is a negative. So negative 0.5 K2 2 times Q1 minus Q2. And then I need to take the derivative of Q2, which is negative 1, equal to the net force on Q2. And so that would be, if you take a look at the mass M2, you'll see that there is U1 acting to the right along X, and there's U2 acting to the right towards X, right? So the net force on M2, the external force, is U1 plus U2. Both are along the positive X. So that should be equal to U1 plus U2. Okay, let's simplify this. So ddt of this term is going to be, but first of all, you can cancel these, this and this. So left with MQ2 double dot is negative, negative, and another negatives. K2 Q1 minus Q2 plus U2. Yes, I'm going to write it exactly like I've written equation 1. I had Q1 double dot on the left side. Similarly, I'll have Q2 double dot here on the left side. So Q2 double dot equals K2 Q1 divided by m. This should be m2, by the way. M2 minus K2 Q2 divided by M2 plus U1 divided by M2 plus U2 divided by M2. Yeah, so those are the two equations. Let me box them. This is equation 1. This is equation 2. Okay, so let's put this in state space form. This is something which we have done in the past. Instead of writing equations as second order equations, we would write them as first order equations, because unless we have them as first order equations, we just cannot do some of the tools which we'll be using in this particular section. So the trick here is to create variables such as typically with x. So x1, let's say, is q1. So here x1 is the position of the first link. X2 is the velocity of the first link. So xq1 dot. X3 is the position of the second link. X4 is the velocity of the second link. Okay, with that, what we can do is we can write the first order equations as follows. X1 dot, so if you take derivative of this, you have q1 dot. I just took the derivative of the first term, but q1 dot is x2. Okay, just from the second equation. Next, x2 dot is q1 double dot. This is just taking the derivative of the second term, but q1 double dot, we know what it is. It's something I've written down the previous page. This is the equation for q1 double dot. So I can just take this. Copy. This is from 1. But the key here is to write everything in terms of x1 and x2. So I can rewrite this as minus k1, just club these things together, k1 plus k2 divided by m1 times, wait, something's not right here. Did I write this correctly? I forgot the bracket. Okay, there's a bracket here which did not copy. X1 plus K2 divided by M. Q2 is X3 minus U1 divided by M1. So this is X2 double dot. My bad. It's X2 dot. Okay, next we have X3 dot. So take the third term here, take the derivative. That's Q2 dot. But Q2 dot is nothing but X4. So that takes care of the third equations. And finally, X4 dot is Q2 double dot. I need to again go back to my derivation, pick the second equation. P Okay, so I need to write everything in terms of x1s and x2s and x3s and x4. So K2 divided by M2, Q1 is x1, Q2 is x3, plus U1 divided by M2 plus U2 divided by M2. This is M2. Okay, so finally, when I need to write the equations, I need to write equations for the first order terms. So those will be x1 dot, x2 dot, x3 dot, and x4 dot. So what we'll do is space here. Okay. Let me try to make some space here. Yes, I'm going to attempt to write this as a single equation, well, single equation in matrix form. X1 dot, x2 dot, x3 dot, x4 dot. You know, these equations are all linear, so I should be able to write them as follows. X1, X2, X3, X4. And so let's start writing the equations down. So the first equation, this should also be something like this, U1, U2. Okay. So the first equation is x1 dot equals x2. So x1 dot should be equal to x2. So I need to put 0, 1, 0, 0, because when I multiply the first row with the column consisting of x, I get 1 multiplies with x2, so I have x2, and I get the first equation. And everything here is 0, so 0 and 0. Okay, next is the equation for x2 dot. So for that, the coefficient in front of x1 is all this thing, k1 plus k2. So let's write that in front of x1. So minus k1 plus k2 divided by m1. Let's make some space here. Okay. So that's the part in front of x1. There is no x2 here, so I just put a 0. Then we have k2 divided by m1 for x3, so k2 divided by m1. Then there's nothing in front of x4, so it'll be 0. And now when we go to u, we have there's a term which multiplies with u1, so the first term would be minus 1 divided by m1 and 0 for u2. Okay, the third equation is x3 dot is x4. So 0, 0, 0, 1. And then for x4 dot, which is this equation, we have k2 divided by m2. There's no term in x2, so 0, minus k2 divided by m2. And then 0 for x4. And then I forgot to put zeros here. And then here we have 1 divided by m1, 1 divided by m2. Okay, let me make this slightly more easier to comprehend. Okay. Okay, so 4 by 4, 4 by 1, 4 by 1, 2 by 1, 4 rows, 4 columns, 4 rows, 2 columns. And then you'll see that when you do this multiplication, it comes out the way you wanted it. Yeah, so what I'll do now is I'll just package all the x's in a variable called x. So this will hold x1, x2, x3, x4. If you put it that way, then you have x dot equals ax plus bu, where it's clear that a is this matrix. So this matrix here is A. This matrix here is B. This matrix is X. And then I forgot to put U. U is U1, U2. So this matrix is U. So X dot equals AX plus BU. This is a linear equation. Okay, and because it's linear, there are so many things you can do with an equation like this. Which we'll see in just a bit. Okay. So let's see what we can do with this. Okay, so first of all, if you have a system AX dot equals AX plus BU, I don't know if you remember this, but you can check if the system is stable or not. Checks the stability of continuous time system. So a system which is uncontrolled would look like this: x dot equals ax, right? Here u is 0 because the system is not controlled. You're not applying any actuation to it. So if you remember from a first course in controls, a system like this is stable if the eigenvalues of A are in the left half plane, or they have a negative. The real part of the eigenvalue is negative, then the system is considered stable. So that's the condition. So to check stability, first thing is compute eigenvalues of A if the real part of the eigenvalues are negative, then the system is stable, else not. Okay, so maybe I'll show you a calculation. But essentially, computing the eigenvalues is basically saying that it's magnitude of A minus lambda I equal to 0. When you solve this equation, eigenvalues. And then there is a command in Python which will help you compute the eigenvalues. Now, a system like this, the spring mass damper, will actually keep oscillating back and forth. So it will not have all eigenvalues in the left half plane. In fact, it will be it will actually be on the y-axis, which means that the system is neutrally stable. Still have a sinusoidal solution. But because you have access to U, or control, you can actually stabilize the system. So we can use control to stabilize the system. So if the system is unstable, we can use control U to stabilize the system. Okay, because U gives you, just like the feedback linearization we talked about, we can do anything we want with U, provided U is strong enough, that is, you have enough torque available to you and or force available to you from the actuators. Now, before you do that, there is something called controllability, which needs to be checked. Okay, just because you have U doesn't mean you can control the system. Now, controllability is the notion that if a system has control U, then it gives you a condition under which the system can be stabilized. If the controllability condition is not satisfied, then no matter what you do with the control U, you cannot stabilize the system. So the definition of controllability is that a linear system is controllable if and only if it can be transferred from any initial state. Okay, so x equals, let's say, x0 to any terminal state, x equals x of t in finite time. It's a nice definition, but it really doesn't tell you how to check for if a system is controllable. So what this definition means is that you need to try applying U. The system is at some state x0. In case of the spring mass damper, let's say that the spring mass damper is at 0, 0. You just choose some condition. And then let's say you want the two masses to be at a different position. You choose those two positions. If you can find U such that you can get from 0 to that particular position, then you say the system is controllable, which means that you need to solve this for that particular U for every conceivable combination of x0 and xt. Okay, that's not very useful in terms of computing if a system is controllable, but there's actually an easy way to compute the controllability. I will not go through the derivation. This is something which we can check quickly in the control system toolbox in Python. You need to compute what is known as so checking controllability. You need to compute a matrix which is called the controllable, which I'll call CO. A n minus 1, B, A n minus 2, n minus 2, B, so on till A, B, B. Okay, note that A here has, the system is x dot equals AX plus BU, where A is n cross n, B is n cross m, X is n cross 1, U is m cross 1. So in our example here, the spring mass damper example, for example, here X was dimension 4, n was 4. So n was 4, and m is the dimension of control, it was 2. So m need not be equal to n. You can have fewer controls than the number of state variables. So this is just for a generic A and B. Okay, you need to control the controllability matrix. Once you get that, you need to check for something. Let me write it on the new page. Okay, so once you found this matrix, which you can now do because you know what B is, you can compute A, B, and you keep doing it till A n minus 1 B. You check the rank of CO. If rank of CO is n, which is the number of state variables, then system is controllable. If rank of C0 is less than n, system is uncontrollable. So what you want to do is you want to check for the controllability. Without the controllability, you do just no meaning in trying to find a control. The way you'll do this in Python is you do not really need to go and find this matrix CO by hand. All you do is the following. You first install the package control. This is a package. There's an equivalent package in MATLAB, which you might have used for your class. Then you import control. Then you can set up the controllability matrix. It is basically control.ctrb. There's a short form for controllability. You give in A and B, which are going to be numeric values as a matrix. And then you can use, in NumPy, there is a command to check the rank of a matrix, matrix rank CO. So we use the controllability, the toolbox to find CO, and then we just use the NumPy package with a function called matrix rank to check the rank of CO. If the rank is equal to n, system is controllable, else it's not. Okay, so the first step. Without this step, you don't want to do the next step, which I'll talk in just of control. Number one is pole placement. Okay, so what we do is we assume a feedback controller k times x. This is a user chosen gain matrix. Okay, now we have the system x dot equals a x plus bu. We sub in the value of u minus k times x. So we end up with a minus bk times x. Okay, so the earlier system was just A, the uncontrollable system, but now the new system with control is x dot equals a tilde x. But a tilde is not just any A. You can actually control how the eigenvalues of A tilde can be assigned because you have full control over the gain matrix K. So by changing K in a specific way, you can ensure that all the eigenvalues of A tilde are on the left half plane. Okay, so what we do is, the idea here is to tune K such that all eigenvalues of A hat or A minus pk, sorry, I should put such that real part of the eigenvalues of A tilde are negative. In fact, you can actually place them wherever you want. So the way to do this is, instead of doing all the math here yourself, it turns out that the control system toolbox in Python gives you a way to do that. So all you have to do is you need to tell it P is locations of eigenvalues. So if you set the locations of eigenvalues in the vector P, then all you do is say K equals control, which is the package, dot place. You provide it with A, the matrix B, and provide with P. This is user chosen. You choose this to be wherever you want. You want them to be at -100, put -100, which will make the system very stable, clearly. This is the gain matrix which comes out from that. So once you do that, you can check the eigenvalues. So the eigenvalues of A minus bk are located at P, which is again something you choose. Okay, so unlike saying that we want the poles to be at a certain place, what LQR does is it creates a cost function, just like we talked about that in optimization. So I'm going to do a special case of LQR. It's called the infinite horizon problem. So in LQR, you'll define a cost. Let's call this the LQR cost. This is a cost. It's defined as the integral from 0 to infinity x transpose qx plus u transpose ru plus 2x transpose nu dx. Okay. So what is q, what is r, what is n? Q, r, n are user chosen matrices. Okay, you get to choose what you want them to be. X is clearly the state. U is clearly the control. Okay, so for example, if you set r equals 0, n equals 0, and you just set q equals, let's say, 1, so then your cost would only involve the first term, and you're saying that x transpose x should be minimized. So what is x? It's basically deviation from 0. So you want to penalize the deviation from 0, and that's what that cost tells you. If instead, if you add q and you also, let's say q equals 0, and you make r equals 1, you're saying the cost is u transpose u, or u square, because r is 1. In that case, you're saying, I want to minimize the u. And so you want to use u as sparingly as possible. But many times you would usually put both of these so that you get a compromise between x, controlling deviations in x and using control. Okay, so we'll talk more about tuning in just a bit. But for this particular cost, I know we've seen something like this before when we talked about optimization. This optimization actually it's possible to solve for u analytically, and it's all possible to do that because the system is linear. If your system was non-linear, like most systems are, you cannot solve this problem analytically. So the solution to this is analytically obtained. Okay, how do you do this? Well, you'll take dj, dq, dj, dx, dj, du, things you do in calculus, right? If you want to minimize a cost, you take the first derivative, set it to 0. That's pretty much what you do. I will not get into the details. What comes out of the optimization is u equals minus kx. Okay. The gain matrix K is minus R inverse B transpose P plus N transpose. Here, note that B is what sits in front of x star u, right? X star equals ax plus pu. So that b is directly from there. But what is p? P is something which is another matrix which needs to be solved for using this equation. It's pretty complex. Pb plus n R inverse P transpose P plus N transpose plus Q equals 0. So we need to solve for P such that this equation is satisfied. In other words, what it says is that in order for the system to be to have a minimum, you need to solve for P in this equation. That's a constraint equation which comes out from the optimization. Once you solve for P, it's as simple as plugging it here to get K, and that K sits in your control term. So the hard part is how do you solve this? This is something which I will not spend time doing, but we will just resort to function within the control package, which will do this for you. Okay, this is just side information. It's actually it's called P is just a matrix. I think it's, what is it called? It needs to be pulse. I know it needs to be, P needs to be semi-positive definite matrix. If you have heard of Lyapunov functions, it's related to that, but I'm not sure. Yeah, I don't quite know what P is in the sense that it has a name, but it is related to, I don't want to give you another terminology. It's related to solving this cost function, which is that, and you will not do that. We will just resort to the controls package to do that for us. So what you can do is, once you have the controls package installed, all you do is say K P E equals control.LQR, and then you send in A, which you know from the system dynamics, B, which depends on the, again, the system dynamics and control. You send it Q, which is something you choose, R, what you choose, N, what you choose. So these are user chosen matrices. This is the gain. This is the solution to, well, I actually know the name of the equation, but I don't know the what P is called, but it's called this equation actually is called a Riccati equation. Riccati equation, probably some guy called Riccati came up with it. And so this is the solution to the Riccati equation. And then the E gives you the eigenvalues of the closed loop system. So what's the closed loop system? It will be eigenvalues of A minus BK. So A minus BK tells you the closed loop system. The open loop system is just the eigenvalues of A, but A minus BK is what we care about. Okay, so let's talk a little bit about Q. Q is N cross N, R is M cross M, and I'll give you what M is. N is, it's N cross M. So you can easily figure that out from this equations. AX plus BU. N is N cross 1, U is M cross 1. X dot is clearly N cross 1. And so this B would be N cross M, and A would be N cross N. So M is the dimensions of control, N is the dimensions of state. In order to figure out Q, you don't have to memorize this. If you look at this equation, X transpose QX plus U transpose RU plus 2N, sorry, some space. Just write it in. So if you write J equation, which I wrote down earlier, it's X transpose QX plus U transpose RU plus 2 X transpose NU. Okay, so from this equation, you can actually figure out the dimensions of Q and R. So since X is, by the way, this is a scalar, right? It's a cost. So 1 cross 1. Okay, X is N cross 1. X transpose is 1 cross N. So it has to be that Q is N cross N. Otherwise, this multiplication won't yield 1 cross 1. Similarly, this will be M cross 1, 1 cross M. And so R has to be M cross M. Okay, we can do the same thing for the last one. X is X transpose and U. X transpose would be, well, U, let's use easy. M cross 1. X is N cross 1, so 1 cross N. So N has to be N cross M. And that's what I wrote down here. So how do you choose them? Typically, what we do is, to make our life easy, we just choose this to be 0. Okay, this is just a cross term. And typically what people do is they choose Q in this fashion. They'll just take some diagonal matrix, usually 1, 1, 1, or identity. Okay, they'll take N, M cross M as something like rho times I, M cross M. So rho basically scales N to R. Now, sometimes what happens is you might have X and X dot have almost the same dimensions. If one of them is state, one of them is temperature, you'll find that this I will not work. So if you have, so occasionally what people do is, instead of having N cross N, they'll normalize it against the maximum value. So they'll take max of, they'll find some, say it's say X1 max. They'll normalize again the max value. So it'll be max of 1, max of the 2, square typical, square, and just so on, just to make it so that it is not badly scaled, so that each of those have about 1 as the norm of that is approximately 1, so it doesn't really leads to poor scaling. Improve scalability. Improve scaling. Have to offer. Here is the first one. Okay, This is not going to do any plots, so maybe I just explain to you what's going on. This is the spring mass damper, so M1, M2, K1, K2. I did a slight this is slightly different from what is in the notes. For the notes, what I did was my state space was, that is X, was position, velocity, position, velocity. Here I did position, position, velocity, velocity. So you will see that some of the rows are switched, but it doesn't really change anything as long as you interpret X accordingly. So let me write this here. State here is X1, X2, X dot 1, X dot 2. State in notes is X1, X1, X2, X dot 2. Okay, so it's the same A, B with some rows and columns switched, which you'll see. Now, I said that you could compute the eigenvalues of A to find the system is uncontrolled. You could use the CTRB function to calculate the controllability, which is going to be computed. Once I do that, I compute the rank using NumPy linalg matrix rank. Then I'll do pole placement. So I want the poles to be at -1, -2, -3, -4, just randomly chosen. It'll actually give me the gain K, which places the poles there. And then it's going to compute the eigenvalues of the controlled system, so A minus BK. Then it does an LQR. It chooses Q as I, same as what I wrote in the notes. Here, R is rho. Rho was 1e negative 2 times I. Same thing I wrote in the notes. It computes gain K and then eigenvalues of the closed system. So I'll run this, and I'll do all these calculations in one shot. Okay, so eigenvalues, uncontrolled system. You see that it's actually 0 for the real part, but there's only an imaginary part. So remember, there's a spring mass damper system. So when you let it go, it just goes back and forth, back and forth. So the system is not unstable, not stable. It's actually called neutrally stable. A spring mass damper, a spring mass system will have a eigenvalue with real part 0. So it just spring back and forth. So the rank is 4, which means that I can control it. Then pole placement gives me this gain. I'm sure that gain has no meaning to you, but if you compute the eigenvalues, it is actually at the location I set it to be in. The eigenvalues are -1, -2, -3, -4. I wanted them there. It actually puts them there. For LQR, it is based on this cost function. That cost function gives a gain K. Just very hard to interpret the gain K, but if you go and look at the eigenvalues, these eigenvalues are much further away, -15, -5, -1, -1. So those two lowest eigenvalues actually determine how fast the system will go to 0. So -1, -1 is probably close to the first one. So it's going to be comparable to this one. So now how do you check this? The only way to check this, I think, is to do a simulation. So what I did was I did a simulation. This simulation is not going to do any animations. It's only going to do plots. So first thing I did was I took the A, B matrix. I put a control of 0. And I said, okay, let's see what happens if the system is pulled apart. And I think I pulled the first mass by 0.5 and let it go. And so if I let it go, then you see this position is wobbly, velocity is wobbly, and it just keeps doing that. It'll just do that forever because the system is neutrally stable. It's going to do that forever, right? There's no damping. There's nothing dissipating energy. It's a conservative system. Okay, so now what control can do for you is it can get you back to 0 as fast as possible. So can comment this, uncomment the gain K. Well, how did I get this gain K? It came from the previous file. I just copy pasted the gain from here to here. Okay, so looks like there's an error. Oh, it's because of this. Okay, uncomment both, and then run this. And now you see that in like 2.5 seconds, the 0.5 became 0 in 2.5 seconds. For the velocity, the blue, you can see that's the second mass it was 0, its velocity didn't matter much, but here velocity went to minus 0.5 to 0. So this is what the control gives you. It lets you, helps you to stabilize the system quickly. And this is only LQR. You could also do that with pole placement. So I think that the remaining thing is kind of self-explanatory, just that a part of this is copy-pasted from the previous file, and then the animations, it's a fairly small file. So you can change the system dynamics here, change the controller, of course, over here, and then copy-paste it here. Okay.